drop something, anything, it falls. Why? You say gravity. Fine, but what is gravity? Where does it come from? Did it exist before the universe began, or did it emerge when matter appeared? Most people never ask these questions. They accept gravity as a given, a force, a law. But Richard Feynman, one of the greatest physicists who ever lived, asked something different. He asked whether gravity is even real, whether it's a fundamental force or just an effect, an illusion created by something deeper. And what he discovered, what he suspected, changes everything. Because if Feynman was right, gravity didn't begin. It can't begin. It's not a thing that exists. It's a description of how things move. A consequence of geometry, of quantum fields, of the structure of reality itself. And this means the question makes no sense. Asking where gravity comes from is like asking where circles come from. Circles don't come from anywhere. They're a property of geometry. They exist wherever you have curves, and gravity might be the same. A property that emerges whenever you have mass and energy arranged in space. Not a force transmitted by particles. Not something created at the Big Bang, but an inevitable consequence of how the universe is structured. And if that's true, then everything you think you know about forces, about causation, about how reality works, is incomplete. Let's start with what gravity appears to be. You drop a ball. It falls toward Earth. Newton said this happens because Earth exerts a force on the ball. An attractive force, proportional to the masses and inversely proportional to the square of the distance between them. This is the law of universal gravitation. And it works perfectly. You can use it to predict planetary orbits, calculate trajectories, design satellites. It's one of the most successful theories in history. But it doesn't explain anything. It describes how gravity behaves. Not what it is, not where it comes from. Newton himself knew this. He said, "I frame no hypotheses about the cause of gravity." He gave us the math. But he admitted he didn't know the mechanism. What is this force? How does Earth reach across empty space and pull on the ball? There's no physical connection, no rope, no medium, just action at a distance. And that bothered Newton. It bothered everyone. Because it seems like magic. How can one object affect another without touching it? Einstein solved this problem, or at least he reframed it. He said gravity isn't a force. It's the curvature of spacetime. Mass tells spacetime how to curve. Curved spacetime tells objects how to move. The ball falls not because Earth pulls it, but because Earth warps the spacetime around it. And the ball is following the straightest possible path through that warped spacetime. This is general relativity. And it's brilliant. It explains things Newton's theory couldn't. The precession of Mercury's orbit, the bending of light around massive objects, gravitational time dilation. It works. But it still doesn't answer the fundamental question. Where does the curvature come from? Einstein's equations describe the relationship between mass energy and spacetime curvature. But they don't explain why that relationship exists. Why does mass curve spacetime? What mechanism causes it? And this is where Feynman comes in. Because Feynman wasn't satisfied with descriptions. He wanted mechanisms. He wanted to know how things actually work at the deepest level. Feynman approached physics differently than Einstein. Einstein thought in terms of geometry and symmetry. Beautiful mathematics. Feynman thought in terms of particles and interactions, quantum mechanics. And he developed a framework called quantum field theory that describes how particles interact by exchanging other particles. Electromagnetism, for example, works because charged particles exchange photons, virtual photons. These photons carry the electromagnetic force. When an electron repels another electron, what's really happening is they're exchanging virtual photons. And those photons carry momentum. Transfer it from one electron to the other, creating what we perceive as a force. This is not metaphorical. This is the actual mechanism, verified in countless experiments. And Feynman asked, can we do the same thing for gravity? Can we describe gravity as particles exchanging force carriers? If so, what would those particles be? And the answer he proposed was gravitons. Hypothetical particles that carry the gravitational force, just like photons carry electromagnetism. If gravitons exist, then gravity is fundamentally quantum. It emerges from particle interactions, not from space-time curvature. You need to pause and think about this, because what I'm about to show you will completely change how you understand forces and reality. Subscribe to this channel immediately. Hit that like button. Share this video with someone who thinks they understand physics, because Feynman's insight goes deeper than almost anyone realizes. Let's continue. Here's where it gets complicated. Einstein's general relativity and Feynman's quantum field theory are both incredibly successful. They both make accurate predictions, but they're incompatible. General relativity describes gravity as smooth, continuous spacetime curvature. Quantum field theory describes forces as discrete particle exchanges. You can't have both. If gravity is curvature, it can't be particles. If it's particles, it can't be curvature. This is one of the biggest unsolved problems in physics. How do we reconcile general relativity and quantum mechanics? How do we create a theory of quantum gravity? And Feynman worked on this. He tried to quantize gravity, to create a quantum theory where gravitons are the force carriers, and he ran into problems. The math breaks down at high energies. It gives infinite answers. Nonsense. And nobody has solved this yet. We don't have a complete theory of quantum gravity. We have candidates. String theory loop quantum gravity, but nothing proven, nothing tested. So we're stuck with two descriptions of gravity that both work, but contradict each other. But Feynman had an insight that goes beyond the technical problem. He realized that maybe gravity isn't fundamental. Maybe it's emergent. What does that mean? Emergent properties are properties that arise from simpler components, but don't exist in those components themselves. Temperature is emergent. Individual atoms don't have temperature. But a collection of atoms, moving randomly, has an average kinetic energy, and we call that temperature. Wetness is emergent. Individual water molecules aren't wet, but a collection of them behaves in ways we describe as wet. These are real properties, useful properties, but they're not fundamental. They emerge from something deeper. And Feynman suspected gravity might be the same, not a fundamental force, but an emergent property that arises when you have lots of mass energy arranged in space. The force we experience as gravity is a statistical effect. On average, a macroscopic manifestation of something happening at the quantum level. Let me give you an analogy. Imagine you have a stretched rubber sheet. You place a heavy ball on it. The sheet curves. Now you roll a smaller ball nearby. It moves toward the heavy ball, not because the heavy ball is pulling it, but because the sheet is curved and the small ball is following the curve. This is how Einstein described gravity. Spacetime is the sheet. Mas curvi said, objects follow the curves. But now ask, why does mass curve the sheet? In this analogy, it's because the ball presses down due to its weight. But what's the equivalent in spacetime? Mass doesn't press down on spacetime. There's no down. So why does mass create curvature? Feynman's answer would be, maybe it doesn't. Maybe what we're calling curvature is actually the statistical result of quantum interactions. Trillions of particles exchanging virtual gravitons. And the net effect, the average behavior, looks like spacetime curvature. The curvature is real in the sense that it accurately describes what happens, but it's not fundamental. It's emergent. Now, if gravity is emergent, then it didn't begin. You can't ask when gravity started because it's not a thing. It's a description, an effect. Whenever you have mass and energy, you get gravity. Automatically, inevitably, it's not created. It's not transmitted. It's just there. Like asking when wetness began. Wetness began when liquid water appeared. But wetness itself isn't a substance that was created. It's a property of how water molecules behave collectively. Gravity might be the same. It appeared when the universe had mass and energy distributed in space. But it wasn't created as a separate entity. It emerged as an inevitable consequence of how mass and energy interact. And this changes the question. Instead of asking where gravity comes from, we should ask what properties of mass and energy give rise to gravitational effects. What is it about particles, about fields, about quantum interactions that creates the appearance of attractive force? Feynman also pointed out something most people miss. All the fundamental forces except gravity have been unified in quantum field theory, electromagnetism, the weak nuclear force, the strong nuclear force. We understand these as particle exchanges. Virtual photons, W and Z bosons, gluons, and these forces have been unified. The electromagnetic and weak forces are actually the same force at high energies, the electroweak force. And there are theories suggesting the strong force joins in at even higher energies, the grand unified theory. So 3 of the 4 fundamental forces are really aspects of a deeper unified force. But gravity doesn't fit, it's the outlier. And Feynman wondered if that's because gravity isn't a force at all. Maybe it's fundamentally different. Maybe trying to quantize it the same way we quantize the other forces is a mistake. Maybe we need a completely different approach. And this is what modern physicists are exploring. Theories where gravity emerges from quantum entanglement, from information theory, from the holographic principle. Ideas that would have seemed crazy to Newton or even Einstein, but Feynman would have loved them. Because they're radical. They're asking the right questions. Let me tell you about one specific idea. The holographic principle. This is the idea that all the information in a volume of space can be encoded on the boundary of that volume. Like a hologram. A 2-dimensional surface containing all the information needed to reconstruct a 3-dimensional image. Physicists have found evidence that our universe might work this way. That space-time itself might be a hologram, an illusion. And gravity emerges from the information encoded on the boundary. This sounds like science fiction, but it's serious theoretical physics, based on insights from black hole thermodynamics. And if it's true, then gravity is not a force propagating through space-time, it's a projection, an effect of how information is organized. And this means gravity is even less fundamental than we thought. It's not just emergent, it's holographic. A shadow of something deeper happening in a lower dimensional space. We're halfway through, and your mind should be reeling right now. Because everything you thought was solid about physics is dissolving. Subscribe to this channel right now if you want to keep exploring these edge of knowledge ideas. Hit that like button, share this with everyone. Because Feynman's legacy is asking questions nobody else dares to ask. And that's exactly what we're doing here. Let's go deeper. Now, let's talk about what Feynman actually said about gravity. He gave lectures, wrote books, and in them, he was honest about what we don't know. He said we don't understand gravity at the quantum level. We have Einstein's theory for large scales. We have quantum mechanics for small scales. But we don't have a theory that works for both, and he was comfortable with this uncertainty. He didn't pretend to have answers he didn't have. And he encouraged others to think creatively, to not be constrained by existing frameworks. He said the first principle is that you must not fool yourself, and you are the easiest person to fool. Don't assume something is true just because it's been taught as true. Question everything, and when it comes to gravity, there's a lot to question. We don't know what it is. We don't know where it comes from. We don't even know if it's real in the sense we think it is. Here's another insight from Feynman. He pointed out that gravity is incredibly weak. Compared to the other forces, it's almost negligible. The electromagnetic force between two electrons is 10 to the 42nd power stronger than the gravitational force between them. That's a 1 with 42 zeros after it. Gravity is incomprehensibly weak. So weak that we only notice it when we have enormous amounts of mass. Like planets, stars, galaxies. On the scale of atoms, gravity is irrelevant. And Feynman asked why. Why is gravity so much weaker than the other forces? And one possible answer is that gravity leaks into extra dimensions. String theory suggests there might be more than 3 spatial dimensions. Maybe 6 or 7 extra dimensions curled up so small we can't see them. And maybe gravity propagates through all of these dimensions while the other forces are confined to our 3-dimensional space. This would explain why gravity appears so weak. Most of its strength is leaking into dimensions we can't access. And if this is true, then gravity is fundamentally different from the other forces, not just in mechanism, but in geometry. It exists in a higher dimensional space. Let me give you a practical example of why understanding gravity matters. GPS, Global Positioning Systems, work by timing signals from satellites. Those satellites are in orbit, moving fast, and they're farther from Earth's center. Both of these factors affect time. Special relativity says moving clocks run slower. General relativity says clocks in weaker gravity run faster. Both effects are real, and they partially cancel out, but not completely. If we didn't account for both relativistic effects, GPS would be off by kilometers within hours. So, every time you use GPS, you're relying on our understanding of gravity. Both Newton's approximation and Einstein's refinement. But we still don't have the complete picture. We don't know how gravity works at the quantum level. And that means there are phenomena we can't predict. Situations where our current theories break down. Like the center of black holes. The moment of the Big Bang. Anywhere spacetime curvature becomes extreme and quantum effects become important. We need a theory of quantum gravity to understand these. And we don't have one yet. Feynman also explored the connection between gravity and entropy. Entropy is disorder, the tendency of systems to become more random over time. And there's a deep connection between gravity and entropy that we're only beginning to understand. Black holes have entropy, proportional to their surface area, not their volume. This is weird. Entropy should be a property of the stuff inside an object. But for black holes, it's all on the surface, on the event horizon. And this led to the holographic principle I mentioned earlier. The idea that the information content of a region of space is encoded on its boundary. And if this is true for black holes, maybe it's true for all of spacetime. Maybe gravity emerges from the thermodynamic properties of information, from entropy. This is a radical idea, but it's being taken seriously because it connects gravity to information theory, to quantum mechanics, to thermodynamics. It suggests that gravity is not a fundamental force, but a thermodynamic effect arising from the microscopic degrees of freedom of spacetime itself. Here's something Feynman loved to emphasize. The universe doesn't care about our theories. It doesn't care what we think is elegant or intuitive. It just is, and our job is to figure out what it is, not to impose our preconceptions. So when we ask where gravity comes from, we might be asking the wrong question. Because the question assumes gravity is a thing that has an origin, but maybe it's not. Maybe it's a property. An aspect of how reality is structured, and properties don't have origins. They just study circles don't come from anywhere. They're a property of geometry. They exist wherever you have rotational symmetry, and gravity might be the same. A property that exists wherever you have mass energy distributed in spacetime, not created, not transmitted, just present as an inevitable consequence of the structure of reality. Now, let's talk about experimental evidence. Can we test whether gravity is particles or curvature or emergent? It's incredibly difficult. Gravitons, if they exist, would be almost impossible to detect. They interact so weakly that you'd need a detector the size of Jupiter to catch one. We can't build that. So we can't directly confirm or rule out gravitons. But we can look for indirect evidence. Gravitational waves. Einstein predicted these. Ripples in spacetime caused by accelerating masses. And we've detected them. LIGO, Laser Interferometer Gravitational Wave Observatory. Caught gravitational waves from colliding black holes. This is huge. It confirms that spacetime can ripple. That gravity propagates at the speed of light, just like Einstein predicted. But it doesn't tell us whether those ripples are smooth curvature or quantized gravitons. We'd need much more sensitive detectors to see that. And we're building them, but it will take decades. Maybe longer. Feynman would have loved this. The fact that we're probing the nature of gravity experimentally, not just theoretically. He always emphasized the importance of experiment. Theory is great, math is beautiful, but nature is the final judge. And we need to test our ideas, push them to their limits. See where they break, because that's where new physics hides, in the gaps, in the anomalies, in the places where our current theories fail. And gravity is full of those places. Dark matter. We don't know what it is. But it gravitates. Dark energy. We don't know what it is. But it affects the expansion of the universe. Both of these suggest our understanding of gravity is incomplete. Maybe we need to modify general relativity. Maybe we need quantum gravity. Maybe we need something completely new. Something Feynman couldn't have imagined, but would have been thrilled to discover. Let me bring this back to the original question. Where does gravity come from? Did it ever begin? And the answer Feynman would give is, we don't know. Not yet, but we're working on it. And the more we learn, the stranger it gets. Gravity might be curvature, might be particles, might be emergent, might be holographic, might be something we haven't thought of. But whatever it is, it's not what common sense suggests. It's not a simple attractive force. It's deeply connected to the structure of spacetime, to quantum mechanics, to information, to entropy. It's woven into the fabric of reality in ways we're only beginning to understand. And that's exciting, because it means there's so much more to discover, so many more questions to ask, so many more mysteries to unravel. Here's what you should take away from this. Gravity is not understood. We have good descriptions. Newton's law, Einstein's curvature. But we don't have a complete theory. We don't know the mechanism. We don't know if it's fundamental or emergent. We don't know how it fits with quantum mechanics. And that's okay. Science is not about having all the answers. It's about asking better questions. And Feynman was a master of this. He asked questions that revealed how little we actually know, and in doing so, he opened doors, created space for new ideas, new approaches, new discoveries, and that's his legacy. Not the answers he gave, but the questions he asked, and the permission he gave others to question everything, to not accept authority, to not satisfied with descriptions that don't explain, to dig deeper, always deeper, until you find something real, something true, something that makes sense of the universe. If this video changed how you think about gravity and reality, you need to do something. Subscribe to this channel immediately, hit that like button, share this video with everyone who thinks physics is settled. Because it's not. We're at the edge of understanding, and the next breakthrough could come from anyone, maybe even you, if you're willing to question, to think, to not accept easy answers. That's what Feynman taught us, and that's what I'm teaching you. So subscribe, share, and I'll see you in the next video, where we'll explore even deeper mysteries at the frontier of physics.